Hey class, this is Mrs. Norris, and this is a quick review of Chapter 5, Section 1. We've been doing some constructions using GeoGebra, and I just want to summarize the theorems real quick, okay? What you should have learned yesterday. If you are given a perpendicular bisector of a segment, in other words, that segment is cut in half by a line that's at 90 degrees to it. So if this is what you're given in the problem, then you remember you can pick any point along that line and it'll create two equal distances to the endpoints of the segments. Okay, sometimes it's helpful when I say these words for you to write them down. Again, I can pick a different point here, still creates two equal segments. I can pick a point at the bottom, still creates two equal segments. It looks like we're making triangles, that's why I made mine dotted in this video here, so that you're understanding this isn't about triangles, this is just about distances, or the length between that point and the endpoints of the segment. Alright, if we do the converse, then we're given those two congruent segments. Okay, that's where we start. And if we draw a line that point contains, then it has to be perpendicular and congruent. Alright, jump into the angle bisector theorem. I know this is kind of quick. It was the second theorem we talked about. Remember, we constructed an angle bisector. These little arc marks are the way that you construct it using a compass. Creating that angle bisector tells me that the angles are congruent right here. If they're congruent, then I can pick any random point on that ray, on that angle bisector, and its perpendicular distances are congruent from each side of the angle. The converse of that, if I draw a line through the angle and I tell you that the distances are equal to the sides of the angle, then you know that the angle's cut in half, or that that's the bisector. Quick review, Section 1. Guest appearance, me. Even more exciting, look behind me. Look who's here. Jesus is here. Okay, I thought it'd be helpful in this section because it's a little bit tough, lots of definitions in this chapter. All right, let's jump to Section 2 now. I'm going to tie this in a minute, but I want you to think about two examples where we're going to use these. One is if three friends were trying to figure out where they could meet up, that would be exactly the same in between their houses. Or, I quote Red, White, and Blue Ash because they have a fireworks display that I went to one summer. It was awesome, by the way. If you get a chance, you should go. What if the city planners were trying to figure out where to set off the fireworks? If they had three areas for people to watch, or three prime seating locations, they wanted to set them off in the center of those three locations, and I'm going to show you how we can use triangles to figure that out. Let's start by introducing a vocabulary word. Usually when we intersect two lines, we just call it an intersection. This time, we're going to intersect three lines. When we intersect three lines, we call them concurrent. That's the description of the lines. And the point where they intersect is called the point of concurrency. You should probably write that down, concurrent, and then draw three lines intersecting in the point of concurrency. Pause if you need to. Now, let's take the example of where we have three friends, or these three prime seating locations for the red, white, and boom. Where would be exactly the middle of those 3 points? Okay, and I'm going to show you how we do it. First thing we do is we make perpendicular bisectors from each side of the triangle. So I'm going to draw these three kind of quickly. This line here is the perpendicular bisector of side AB. This line here is the perpendicular bisector of line AC, and this is the perpendicular bisector of line BC. What happens is they create a point of concurrency. This point of concurrency is called the circumcenter. C-I-R-C-U-M-C-E-N-T-R. This is where the perpendicular bisectors of the three sides of a triangle meet. Once we have that point, we draw it. Let's get rid of the perpendicular bisectors for a second. And what happens is they create equal distances to each of the vertices. And this is where the example ties in. So if I drew a triangle connecting the three places where you wanted to, of course you would do this with a computer or even with GeoGebra, the city planners could measure the distance from A to B and from B to C, etc. They could draw perpendicular bisectors from each side of the triangle, and this blue dot would be where the fireworks would be equal distant from all three sections. We call this the circumcenter. So when you're drawing this, you may want to go back under the Circumcenter Theorem, which is what this is about. You may want to draw the given. This is your given picture. If you're given three perpendicular bisectors, then their point of concurrency is called the circumcenter. Then, next to that, draw a whole separate triangle and put your point down, and then make three lines that are the distances from that point to the vertices. Okay? This is called the Circumcenter Theorem. The circumcenter is equidistant from each vertex. Okay, if we were to make a circle using our compass, we put a center, our centered at P. These red lines are the radii, the radius of the circle. So we could draw a circle around, centered around P, and it would go through each of the vertices. This is called the circumcircle. Similarly, we're going to draw what's called the incenter. This time we're going to construct the three angle bisectors. So through each vertex, we're going to make an angle bisector. There's the first one, there's the second one, there's the third one. When they intersect, their point of concurrency is called the incenter. What's special about this point? Well, draw this picture for the Incenter Theorem. After you draw this picture, draw another triangle named ABC. Let's get rid of the angle bisectors, but leave point P there. What's special about these is they're equal distance or equidistant to the sides of the triangle. So the other one was equidistant to the vertices, this one's equidistant to the sides. This is called the Incenter Theorem. It says that the incenter itself is equidistant from the sides of a triangle. Okay, we can also make, using these three red lines here, remember these are the same and they're centered about some point P, so we could draw a circle with a radius that's equal to this red line here. Drawing that circle creates what we call an inscribed. Okay, make sure that you have the Circumcenter Theorem and the Incenter Theorem down for this section. We're going to mess around a little bit more with GeoGebra tomorrow, and we'll do some book exercises from both sections, and talk to you soon. Okay, before we go, just one more guest appearance.
Hi, good luck.